which is describing or gathering and describing data. You might find this is kind of an easier chapter compared to some, especially because you might have done some of it in previous classes. So to start with, we'll talk about we'll talk about experimentation. So we did a lot of things with very mathematical settings where we looked at probability distributions, and I'd say, okay, let's say f of x is 1/9 x squared, and that was the length of the prison terms. Or we said maybe this thing has a binomial distribution, etc. But usually we're not going to actually know a true underlying probability distribution. We're not going to know exactly that something is binomial with a probability of 0.55 or something like that. Instead, what we're going to do is we're trying to figure out what that underlying probability density function would be through conducting studies, collecting data, etc. So to start with, we have some terminology. Population consists of all of our possible observations from a particular probability distribution. Or here we're talking about an underlying probability distribution. Most of the time we just think about it as the set of all the possible observations of something we're interested in. So like in example 153, an investigator wishes to know what proportion of voters in the U.S. will vote Republican. So the population would be all the voters in the U.S. So that's what a population is. It's everything that you could possibly be interested in, or everything that you are interested in. Whereas the parameter is some property or underlying number of this probability distribution. So in example 153, the parameter, what we'd be interested in knowing, would be the proportion of all the voters who would vote Republican. So the population is all the voters, and the parameter is the proportion of all the voters who would vote Republican. So in our next example, a toothpaste company would like to know what proportion of dentists recommend the brand it produces. So identify a population and parameter. So we want to know what proportion of dentists. So I would think the population would be all dentists. And again, the key word for population is that all. Not just some small set, but all dentists. The parameter, well, it said we want to know what proportion. So it's the proportion of all dentists that recommend this brand. And then if you guys aren't familiar with it, what is a proportion? Just to make sure, proportion is like a percentage, but in decimal form. So like 30% would be 0.3. So we've talked about the population, like in this case, the population would be all dentists. But usually it's not going to be feasible to collect data from everyone in a population. So we're not going to go and talk to every dentist. Why wouldn't we go talk to every dentist? Okay, it would take too long. It's going to be too expensive because time is money. Okay, there's just too many dentists. And so in most cases, it would be almost impossible to actually get data on the entire population because it's just going to be too big. You're not going to have enough time or money to get data on everyone. Now, if you could get data from everything, then you could figure out that true underlying probability mass function or density function. But we can't. So instead, what we'll do is we'll take a sample. So a sample is just any subset that we collect data on. And then from that sample, we can compute a statistic. So we could calculate like the mean or the average or something from our sample. And we can use those sample statistics to try and estimate values about our population. So a statistic specifically is a random variable. We compute it based on data in the sample, and we can then use it to make inferences about the general population. And just as kind of a side note, there are two different branches of statistics, so we kind of do both in here. Inferential statistics is when you try and figure out properties of the population based on the sample. And descriptive statistics is when you just try and summarize or describe the data numerically or graphically. So let's make ourselves a note because this is something that people usually forget. So statistics are from samples, and parameters are for populations. Either way, statistics or parameters are some value that you're computing. So it could be either the average, you can find the average of the sample or the average of the population, or the standard deviation of the sample, standard deviation of the population. So this is an example here, okay, where if you look at the blue line is the underlying probability distribution, the actual curve. And so that's kind of like our true values. But when we get the data from our sample won't line up exactly with the true probability distribution because it varies based on who was in my sample. But you should see that the data in your sample should be kind of close to your true probability distribution, or what the true population values would be. So as far as choosing a sample, we have what's called representative samples. So when our sample is representative of the population, so representative of the population means the sample is similar to the population. Or it has kind of similar properties. Then estimating parameters for the population from the sample is justified. Or in other words, we want to pick samples so that our samples will be similar to the population. So if we wanted to try and figure out who was going to vote Republican in the next election, or what people were going to vote for in the next election, but I only went to a small town that had all Democrats and took my sample there, would that be representative of everyone? No. Okay. So you want your samples to be similar to your populations. If a sample is poorly chosen, then any statistics you calculate from that sample are going to be poor estimates of your population parameters. So this is a good example where in the 1970s, Ann Landers asked her readers, if you had to do it over again, would you still have children? She received over 10,000 responses. Now 10,000, you think, that sounds really big and this is probably going to be accurate. Right? And 70% of the people said no. Now thinking about that, if you think about your parents or different people you know, you think most of them would probably say yes, right? That just seems shocking that 70% are saying no. Or that means that 30% are saying yes. So in this case, her population was all North American parents. Or at least that's probably what she'd be reporting, that all the parents, she asked all the parents. Okay. And the parameter is the percentage who would not have kids if they could do it over again. So first we might ask, well, did her sample adequately represent the population? So let's go ahead and have you guys turn on your mics and brainstorm here. So you could give me a few different things. Do you think, not even based on the answer, but do you think that because she asked her readers and she received responses, okay, and 70% said no, what are you guys thinking about? Like, would her sample represent all the population? So brainstorm to do this. So again, only her readers saw the question, and that's not everyone in the United States. It's probably going to be specific people that were subscribing to this one magazine for one specific reason. So maybe they just didn't like kids. Maybe it was, like I said, maybe this was a how to leave your kids at home and go to work thing or something. I don't know. And only the people that actually responded are part of this. So people with strong feelings are more likely to respond. So it's really not going to represent the population. So how would we select a more representative sample to carry this out? Okay. What we'd want to do is we want to ask people from, or let's say ask all kinds of people from the U.S., okay, not just her readers. And one of the things that we're always going to want to do is get a random sample. So we would want to randomly sample people to ask. And we want to make it really easy for them to respond. So again, we don't want it to be any kind of effort for them to respond, because only people with passionate feelings will actually bother responding. Now, as a little note here to reassure you that your parents do love you and they weren't just lying, another magazine actually interviewed 409 randomly chosen people, and this was just from Kansas City, not from the entire U.S., but out of their 409 people, 94% said that they would have children again. So instead of 30% of her readers, 94% said that they would have children. So the randomly chosen samples are always going to give you better results. So just to talk about random samples, to ensure that our sample is representative of our population, a random sample should be used. Or in other words, the elements in the sample should be chosen randomly, using some kind of probability-based mechanism. Because if a sample is randomly chosen, then human choice is not part of the selection process. One of the ways you can do that is you can assign every human a number, or all the objects in the population a number, and then use a random number generator to choose which people you'll have in the sample. And there are different kinds of random samples. Usually we'll just use a simple random sample, which means that every object in the population is equally likely to be chosen. So here's a few different possible samples, and we'll talk about them, see if they seem good or bad, what would be bad about them. So in this one, 4 students want to determine which Logan grocery store has the lowest prices. Each student makes a list of the items he buys most often, and the students compare prices on those items at the local stores. And number 2, a teacher wishes to know what proportion of the students that take Stats 3000 are female. So she teaches one section in the spring, so she chooses this section for her sample. Do you guys have any thoughts on that one? A sample of convenience. So it's called a sample of convenience because it was very convenient for her. She was already teaching the section. She just kind of went and saw how many were females. So anytime you have a sample of convenience, it's usually a bad sample. A much better thing would be to either check throughout the entire year or check over a couple years, randomly select a couple classes to go check. But doing just one little section because it's convenient isn't going to work well. So this next one is kind of a review. It's just another way to write it. Whether you're thinking about collecting data or you're thinking about probability distributions. So again, our population is a set of all of our people, items, events, objects, etc. that would be of interest. So for example, population could be everyone in the US, or every Honda car built in 2013, or every English major at 4-year universities in Utah. Just whatever you're interested in. Your sample is going to be some smaller part that you actually collect the data on. So for example, you could do every 1,000th person in the US, or every 500th car to come out of the Honda factory, or 300 English majors selected from 4-year universities, etc. So the population is always bigger. Everything, the sample is some small part of that. When you collect a sample, you'll get observations out of it, and that will be called our data set. And we use the notation in this class of x1, x2, up to xn, so each little x value would be each observation. Your data can either be categorical or numerical. So categorical, sometimes called nominal or qualitative, means that you fall into one of several categories. Binary is kind of a subset of that, of if you fall into only 2 categories. And numerical data, or quantitative, is your data is either like integers or real numbers. It's very numerical, and you can perform arithmetic operations like adding or averaging, and it makes sense to do that. So let's look at this example. I want to know the final grades as a percentage of all the students in the U.S. in intro stats courses. So what would be the population? The population would be all U.S. students in intro stats. So what would be a possible sample? Now there's not a correct answer on this because you could say quite a few different things. But we do want to make sure any samples we pick would be random samples. And so then just kind of pick how many people you might want to talk to.
All of them.
Okay, well you talk to all of them, and when you're done, let me know. And I'm only going to pick any random number, so, well, not a random number. You do this based on how much money you have. But let's say for this study I have enough for 500. So let's pick 500 random students. In intro stats. Now, if I only picked these 500 students from Utah, would that be a good sample? No, because those are just students from Utah, and they might be different from students in the entire U.S. So we would want to make sure we're picking students from all around the nation if that's what we want our population to be. Let's see, so what would be our variable? Our variable would be our final grades. And it said it was the percentage. So instead of like an A is your final grade, 99% is your final grade. So is this variable numerical or categorical? Okay, so you said both, so explain. So I would go with numerical because it said we're checking the actual percentage. If I said check the letter grade, what would it be? Then it would be categorical. So our
GPA letters.
Yeah, GPA letters or GPA letters would be categorical. Actually, GPA, well, maybe not. Okay, it is numerical because I said we'll look at the percentage, and those are numbers. So let's look at these and decide if they're categorical or quantitative. So go ahead and shout them out. So the amount of carbon dioxide produced by a car. First of all, does anyone actually know how you measure that? It is parts per million. I had to go look it up because I didn't know. So that's how you measure carbon dioxide. So based on that, what would you think it would be? Okay, I agree, numerical. Color of a car.
Quantitative. Categorical.
Categorical. Breed of a horse. Categorical. Length of time to graduate from college. Numerical. My favorite example, your social security number. Okay. It is actually, well, okay, so first of all, tell me why you say categorical. Because that is a good response.
Because I don't think it's based on, I don't know. Good question. I just thought it was.
No, keep.
Add an average and have it make sense.
Yeah.
That's what
Based on where you're born.
Okay.
Yeah, and it's not gonna be in series, right? It's not gonna be in a series.
Uh-huh. Okay, so based on what you guys are saying, and Justin here was saying, it doesn't make sense to add or average it. Like, so if you tell me your social security number, does that really tell me anything about you? In a numerical sense?
Yeah.
It might say where you're from. I'm not really sure how those work, but is where you're from a numerical type of thing? Like, even where you're from is more categorical. And so this is actually what we say here is I think we could agree that it's not numerical, because if we add our two social securities, or if we take the average of our social security numbers, does that tell us anything? No. And so it's definitely not numerical. So some people say categorical, but the best way to say or classify would be it's an identifier or a label. It's a really good way to keep track of people in your study, but it doesn't actually really tell you much about the person themselves. And let's see, the length of your favorite song would be okay, yes, numerical, and the artist of your favorite song would be categorical. Now, as far as why do you truly care what they're going to be, it makes a big difference about with how you'll design your sample. Okay, when you have categorical versus numerical data values, it changes how you graph them, what kind of graphs you can use to represent them. It changes what kind of tests you can do later on. Basically, it changes everything you can do statistically on this data based on whether or not it's categorical or numerical. So in section 6.2, we talk about how to present data. Because if you just go and collect the data, it's not going to mean anything to you. Somehow you have to summarize your data. And you want to do it in a nice, clear, organized way. Now, keeping in mind again, whether or not your data is categorical or quantitative, that's going to affect what types of things you use to summarize it. And again, keeping in mind that if you do a bad job of making graphics, that can exaggerate relationships or obscure information, or really you can mislead people with graphics that are poorly made. Whether you're doing it on purpose or by accident, it's not a good idea. You should try and make your graphs as accurate as possible. So if you have categorical data, there's 3 different ways you can do it, and you've probably seen almost all of these before. Okay. So looking at this example, these are the market shares for the major GPS brands sold in the U.S. So you have 47% for Garmin, 19% TomTom, etc. So you can see down here in the bottom, we have a nice little pie chart. With the pie chart, each slice is kind of representative of the percentage in that category. Okay. Above it, we have what's called a bar chart. And you just put a bar for each category up to its percentage. So Garmin had 40-some%, you go up to 47%. Super easy. And what's the only difference between this first one and this second one? They switched the order of the last 2 categories because now they're all in descending order. So this is a special bar chart called a Pareto chart. And a Pareto chart just makes sure that they're all, again, in descending order. So you have the highest all the way down to the lowest. And sometimes that's kind of the best way to represent it so you don't hide any categories, or you don't want to necessarily put the one you're interested in very last so people pay more attention to it or something. And just as a note, one of the ways that bar charts could be deceiving is if you truncate the axis or do a shorter axis. So notice here you have these A, B's, and C's, and C looks like it's about twice as tall as A, right? So I think that twice as many people were in group C. But look at the actual frequencies or percentages. So C is at 100 people, but A is still at 87 people. So are there twice as many people in C? No, you can see if you actually do the chart all the way from 10 up to 100, that C doesn't really look that much bigger than A or B. And so if you truncate the axis, again, people will look at it, just kind of glance at it, and they might get the wrong idea. So don't truncate your axes. Now, numerical data, again, so if you're dealing with numbers, we can do what's called a histogram. Let's see. So if I just scroll down quickly, these are all pictures of histograms down here. Notice they all look like bar charts, right? But they are for numerical data, so they take a little bit more work. So what we'll do for a histogram is you look at all your data. So if I'm looking at, let's see, so this example, we have IQ scores for 60 randomly chosen 5th graders. We want to make a histogram. And here are all the IQ scores. So if you're looking at all the IQ scores, what we'll do is we'll kind of divide them into classes. So we'll say from 10 to 20, 20 to 30, 30 to 40, etc. And then we'll count how many people are in each of those classes or bins, and then we'll draw our histogram based on that. So let's look at our notes. So the histogram is composed of bins or classes where each area is proportional to the number of data observations within each bin. And one of the things that kind of helps the most is to have all your bins have equal width. It's not necessarily required, but it's very common. And just as a note, your bin width, you do want to choose that carefully, because if it's too wide or too small, it makes it harder to actually kind of get an idea of what's going on with the population. So again, if we have these IQ scores and we want to do a histogram, the first thing you want to do is always reorder them. So actually put them in order. And then we'll pick some bins. Now this isn't a right or wrong thing, or there's not one that you need to do. So we'll make up our bins, and then in each one we'll do a count, or the frequency. We'll see how many of those there are in each category. So for the bins, let's see, it looks like we go from about 80 to 145. You could do this by 15. You could do it by 10. You could do it by 20. You could do it by 7, 17. I'm going to pick something I can count by easily, so I'm just going to do it by 10 because that's really easy for me and I'm doing it by hand. So I'll go from 80 to 90. Notice I'm not going to include 80, but I will include the 90. And come up and count everything from 80 to 90, including the 90. So it looks like we have 4 of them. And then we can go from 90 to 100. And notice you can only include the 90 once. So you can decide if you want to include it on the left or the right, but only count the 90s once. So then we want to go from 90 to 100, not counting 90. So 90 to 100, that looks like another 4. And 100 to 110. 110 to 120. 120 to 130. 130 to 140. And I need to go 140 to 150. So go ahead and count them on your own. See what you have. Make sure you're not double counting anything. And so I get 16, 14, 12, 8, and 2. So once you've counted all of these, you come over here. And you do always have to label everything. So let's say our vertical will be our actual test scores, or I guess these are IQ scores. And I'll put an 80, 90, 100, 110, 120, 130, 140, 150. I guess I'd make that 70 there. And then you can decide what you want to count by on the side. I need to go from about 0 to maybe 16 or 20. So I might do every line count by 2. So like 2, 4, 6, 8, 10, 12, 14, 16, 18. And then from 80 to 90 we have a count of 4. So from 80 to 90 you'll go to a height of 4. It helps to see if you shade it in. From 90 to 100, you also have a height of 4. From 100 to 110, you're going to go up to 16. Then we'll have 14 and 12, 8, and 2. So now with our histogram, we can look at this and kind of see, okay, it looks like our most common values are around like 110 to 120 seems to be pretty common, or maybe even 100 to 130. And you can then say other things about your distribution. One thing I didn't do is I didn't label my y-axis that this is the frequency, or the count of how many people were in each group. So we do one histogram by hand. Everything else though we're going to use software. So in this example, these are the IQ scores from just our last example. But I chose different bin widths. So we did a bin width of 10. So let's make a note here. This one we did a bin width of 10. Just because I picked 10 because it's easy for me to count by 10. Okay. So here we did bin widths of 2, 7, and 20. Okay. So how did our histogram change? Like when you look at the 2, that's so small that we have just lots of spikes and it's kind of hard to see the overall shape. The 7 seems to be pretty good, I think. I can tell kind of what the most common is and kind of get an overall shape, idea of the shape. But a bin width of 20 is that one is helpful. It seems like it's just so big you can't even see anything anymore because the rectangles are all so wide. So I would say like this bin width of 7 is probably the best option. It seems to look the best, right? And sometimes on Omega you can even change the bin widths, and sometimes I've had to play with them a few times to find something that I think kind of looks good and gives a good representation of the data. So now that we've done that, we're going to learn about outliers. So an outlier is a data point that doesn't seem to fit with the rest of your data. So outliers could be a misrecorded data observation. And in that case, if you know that it's just misrecorded data, you could correct it or remove it from the data set. Usually, though, outliers can actually represent true variation in the population. And so in this case, the outlier would tell you something about the population, and we don't actually want to remove it from the data set. So a good example of that would be if you were looking at people's heights, okay, and then, like my brother-in-law happens to be 6'9". So he's definitely an outlier. He doesn't really fit with the rest of us, but he is a true value. He's an accurate value, and he represents variation in the population. We wouldn't want to take him out. But in this example, I asked students once, what is your height in inches? So for example, like 5'9" was supposed to be 69 inches. And this is the data I received, 5'5", 62, 62, up to 76. So here's our nice little histogram. Here's the little people down at 5 inches, and then all the rest of the normal people. So what do you think actually happened here? Okay, was anyone 5 inches tall in my class? No, and so why did they tell me 5?
Like 5 feet exactly, or 5'5" or something like that.
Yeah, so
It wasn't recorded how it was supposed to be.
yeah, so Justin here thinks that they were probably 5 feet. And wrote 5 instead of 60. Okay. And so yeah, they just read it, they weren't really paying attention, and they just wrote down a 5 because it was easy and they didn't have to try and figure out how many inches that was. And so in this case, when I first looked at this, I said, okay, obviously no one in my class is 5 inches. Those are not true values. And because they're not true values, I'm going to want to remove it. And so I would remove the outliers. If I'm really, really sure that that's what happened, I could maybe replace the 5 with 60. If I'm really sure that they were just 5 feet and just not paying attention. Hopefully they weren't like 5'5" and just really not paying attention and not caring, just wrote a 5. But we'd probably just remove the outliers in those situations if we know that they are mistakes. And so then we just make our histogram without the outliers. It looks much more normal. Everyone's heights are from like 60 or 5 foot up to like 6 something. And that looks right. But let's just make ourselves a note that we only remove outliers if we are sure they are mistakes and not true values. Then once we make a histogram, we might want to look at the shape of the histogram. So there's a few different things we can look at here. One is symmetry. And these are things I've been kind of saying throughout the entire semester, we just haven't learned them yet. So a distribution can be symmetric, left skewed, or right skewed. So in this first row we have some symmetric distributions. Now this can apply to whether you're actually talking about sample data, which is going to look more like a discrete bar graph, or if you're looking at true probability distributions. These descriptions apply to them all. So symmetric is, what it sounds like. It's the same on the left and right. A left skewed distribution means that it has a long left tail, is the way I always think about it. So left skewed kind of means that you have this long tail. So you have a lot on the right and not very much on the left. So a lot on the right and then it kind of slopes down to the left. It's kind of that long tail. A right skewed distribution means you have a long right tail. So you kind of have a lot on the left and slopes down to the right. So it's that long right tail. So a few notes. If you have a left skewed distribution, sometimes called a negative skewed, then most of your bulk is going to be in the right side. So here's your left skewed here. So the right side has most of the data, but there are some extreme low values in the left. Now, since you have so many people on the right side, you would expect probably a higher average, right? You'd expect your average to kind of be over here on the right side. But or probably like here. But what happens is you have some really low values over here, and they kind of pull the average towards the low values or towards the outliers. And so anytime that happens, your average is going to be lower than you might expect because the average kind of gets pulled down. And so it turns out that your mean will be less than the median, or the mean will be lower than the median because the average gets pulled down by those outliers or those extreme low values. So let's try and think of some examples of when you'd have a left skewed distribution of life. So most people have high values, but there's a few people with low values. So I'm a teacher, so I always think about things for teaching. So the first one I thought of was scores on an easy test. Because most people will have high scores, but a few people just still didn't study and get low scores. Okay, one someone said last time was the age when people die. Because most people will be 70s plus, but some people are dying as children or teenagers, middle-aged, etc. And so more scores are up high, there's a few down low. In a positive or right skew distribution, most of your values are in the left and just a few up on the right side. Now, if you think about it, you probably expect your average to be kind of down here, but these extreme values kind of pull the average up a bit. And that means that your mean or your average will be higher than the median. And we'll actually talk about this a little bit in the next section of why the mean changes and the median doesn't. But for some examples of a right skew distribution, we could have, okay, let's see, we want lots of people to have low values. So these could be scores on a hard test. So most people do poorly, but a few people studied a lot and do really well. My favorite example, though, is people's salaries. Because most people have kind of, like those low, normal, average, middle-class salaries, but you have a few really rich people out here. Now, if you include the really rich people into your data sets, are they going to pull the average up? Yeah, by a lot. So we talked about symmetry. Then you can also talk about modes. Modes is just very graphical, like symmetry and modes are both, like you just kind of look at the graph. It's not exactly correct. You might kind of disagree with me a little bit, especially on modes. Because it's kind of just general shape. So unimodal means that you have one mode. So I used to kind of come in and sketch kind of the overall shape. So overall shape, that one looks like it has one mode, and this one kind of has one mode. Those all have one mode. Bimodal means that you have two modes or peaks. So on this one, like, you kind of go up and then down and up and down. So you kind of have two modes. Or up, down, high, low, high. So those all have two modes. And multimodal is 2 plus modes. And so technically bimodal does count as multimodal, because multimodal is just anything that has more than one. But on this data set, I might say you have 1, 2, 3 peaks. And this one might be like 1, 2, 3 again. Sometimes people do look at these and disagree with me. Like, maybe someone might say this one has 4 peaks if they include that one right there. Or they might try and argue that it only has 2 peaks. Like, maybe you just go 1, 2. And you can argue that as long as you have a rational argument for me.